We're going to look at what are called transformations. So we're going to look at a function called a parent function that is the most basic function in a particular type. And then we're going to add or subtract or multiply, divide, add some negatives. And depending on where you put those numbers, that's going to move the function around. It'll change the coordinates in a very specific way. And the nice thing is, those transformations are the same regardless of the function. You're going to have the same basic movements depending on where you put those numbers. So our calculators are really going to help us out here. But if you look at the top of this page, we have the parent function x squared. So I'm going to graph x squared. And then I'm going to go to the table. And we know what a parabola looks like, or a quadratic. It has the shape of a parabola. So we're going to center all of these graphs, or all of these tables, around the minimum or maximum point. So this one is -3, 9, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, and 3, 9. So that's going to look something like this. Okay. Now down below, we're going to graph f of x plus 4, which means we're going to replace the x in f of x with x, is it plus 4? X plus 4, yeah. So it's going to look like f of x plus 4. So there's a difference between x plus 4 squared and x squared plus 4. And you have to understand this distinction to be able to do anything in transformations. This one is saying change all of your x's by 4 and then plug that number into the function f. So which one of these is f of the quantity x plus 4? Which one of these? I hear both. I hear top and bottom. So the instructions here, well, remember, so x is an input, and f of x is an output, also known as a y value. So we can either change the x's before we plug them in, or we can plug in x's and then change the f of x's, or the y values, after the squared has been calculated. And this one is saying, take our x, add 4 to it, and then plug it in and square it. So it would look like this. So I'm going to go in my calculator, and I'm going to type parenthesis x plus 4, and then square it. And push graph. And I'm going to go to my table of values. And now my minimum value has changed. So I want to center it about that. So this would be -6, 4, -5, 1, -4, 0, -3, 1, and so on. And that graph is going to look like this. So what is the difference between f of x and f of the quantity x plus 4? How did the graph change? What is the difference between this graph, which is f of x, and this graph here? It moved it to the left 4 units. Everybody see that? By adding 4 on the inside, I moved the graph to the left 4 spaces. Okay? So for the next one, this is x minus 2 squared. I'm going to look at my table of values, and again, the minimum has changed. So I'm going to center it right there. So my table of values would be -1, 9, 0, 4, 1, 1, 2, 0, 3, 1, and so on. And that graph looks like this. What effect did f of x plus 2 have on the function? It moved it to the right. So move to the right, oops, 2 spaces. Does that make sense to everybody? Anyone not able to do that on their calculator? Okay. So let's look at the next one. So this one says f of x plus 6. What would that equation look like? Oh, minus 6, thank you. What would that equation look like for a quadratic? It's going to be x squared minus 6. So this is just a set of instructions that says, take your x values, plug them into the function, and the function is x squared, so we're going to take our x values and square them. Once I've calculated that, then I'm going to subtract 6 off of that whatever that answer is. So in my calculator, this would be x squared minus 6. Push graph. I can go to my table. So this is centered negative 3, 3, negative 2, negative 2. Oops, negative 1, negative 5, 0, negative 6, 1, negative 5, and so on. And the graph looks like this. What effect did f of x minus 6 have on the graph? Moved it down 6. Okay, I want you to do the next one on your own. I'll pause the video. Okay. On the next page we have f of x plus 3. What would that look like in equation form? What would we put into our y equals? Is it going to be quantity 3x squared, or is it going to be 3 times x squared? Well, if we look, it says f of 3x. So I'm going to replace my x with 3x and then plug it into the function. So this is what it looks like. Where an x used to be, I put a 3x, and once I multiply by 3, then I square it. Down on the one below, it's 3 times f of x. So that would be 3x squared. What would this one look like? Y equals x over 3 squared. What would this one look like? Y equals x squared over 3. So that's the difference between changing the x's before I square it and changing the y's after the square has been performed. Okay? Go ahead and fill out all of those tables and graph all of those functions. And then we're going to come up with a new set of rules. These are not translations. Okay, these are some other sort of transformation. So let's look at these first 4. And I'm going to draw the parent function on all of them. You don't need to. So this is what x squared looks like. The first one is 3x squared. What's the difference between x squared and the quantity 3x squared? It's a lot thinner. Okay? How do I... Well, if you looked at your values, the first one, So the normal -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. That's the original x squared equation. The new one is -2, what did you get? 36, -1, 0, 0, 1, 9, and 2, 36. So you can see that the y values on the transformed function are much, much higher than the y values in the original function. What do you... Oh, okay, yeah, that'll take me a minute to put together. I'll just take it to the office. Thanks. Okay, so this one is a lot steeper. Okay, if we move over to x over 3 squared, what did that look like? It was really wide. Yes. Oh, I can only see one hand. I thought you were... Okay, what about 3x squared? What did that look like? It was much steeper. And then what about x squared over 3? It was wider. Now, are they the same? Well, sorry. Are these two the same? Not quite. Which one is taller? The first one ended up being taller. Are these two graphs the same? No. Which one is wider? The top one is wider. So let's think about what's happening. Remember, if the transformation occurs inside the parentheses, you're changing the x values. Oh my goodness. When did she leave? It is open. Where did you go? Where did you disappear to? Oh. You just up and walked out? Normally you ask for permission and use a hall pass. Okay. So on this first graph, we are timesing the x's by 3. Anytime you multiply a function, those multiplication numbers are what we call a scalar. You're going to scale the graph. Now, if you're building a house and you have blueprints, it doesn't make any sense for the blueprints to be the size of the house. So you scale them. You make the blueprints much, much smaller so that you don't have to lay them out. It just wouldn't work. 1 inch equals 1 inch. That doesn't make any sense. So what we're doing is we are scaling the graph. And multiplying by the inside, on the inside scales the x's. Multiplying on the outside scales the y's. But remember that x's work backwards and y's work exactly like you think they would. So in this second graph here, we are scaling the y's by 3, which means we're going to stretch the y values 3 times higher than they were before. And that's why 3x squared is thin. But up here, we're going to scale the x's by 3. But the scale factor inside works backwards, so that means we're going to smash the x's 3 times thinner than they were before. So if you stretch the y's by a factor of 3, it's going to have close to the same movement as smashing the x's by a factor of 3. Now, are they the same? No. And the reason they're not the same is because this is an x squared graph. There are some graphs where a 3-time compression on the x looks exactly the same as a 3-time stretch on the y's. Sometimes one is taller than the other, and sometimes it's the other way. It just depends on the function. So over here on the other side, what's happening there? What does dividing the x's by 3 do? It stretches the x's 3 times wider than they were before. So this graph, the x's got 3 times closer than they were originally. And on this graph, the x's get 3 times wider than they were originally. On this graph, the y values became 3 times taller. And on this graph, the y values became 3 times shorter. So it's essentially moving closer to the y-axis or away from the y-axis or away from the x-axis and closer to the x-axis. But in general, timesing by 3 on the outside will do almost the same thing as timesing by 3 on the inside. So scaling the inside and scaling the outside by the same number have the same basic movement. They won't, rarely will they be exactly the same, but they'll be close. Okay, what about the last two? What happened here? So here's my original graph. How does f of negative x change? Not this one. So if my original was negative 1, 1, 0, 0, and 1, 1, what does the transformed one look like? Nothing happened. Okay. What about negative f of x? Here's my original quadratic. What did the negative f of x do? So this equation here, negative f of x, says plug in your x's. When you have your y values, change the sign of the y values. So every positive y value now becomes a negative y value. So that reflected, this is a reflection across the x-axis. So what happened on f of negative x? Did it reflect? It did, but it reflected across the y-axis. Well, if you reflect x squared across the y-axis, what do you get? The same thing that you had before. And this says, change the sign of all of your x's before you plug them in. So if I had 5, if I plugged in 5, that's the same as plugging in negative 5. So it moved it there and then up. This point moved to here and then went up. So number 7, what effect does f of 5x have? It compresses the x's 5 times. Okay, number 8. Expands the x's by 4. Number 9. Are we changing the x's or the y's on number 4? Or number 9, sorry. The y values, are they going to stretch or compress? Stretch by a factor of 7. Number 10. If you change the signs of the x's, it actually reflects across the y-axis. So number 11 would be reflect across the x-axis. And 12 has 3 transformations. What are they? Left 3. Wait, follow the order of operations. Left 3. Reflect across x-axis and then move up 2. And you have to perform them in that order. Left 3, reflect across the x, and then go up 2. Okay, turn the page. Okay, for these, you have a graph, and then you have a transformation. So how would I change this graph to represent f of x plus 2? This graph would be moved up 2. So you would just draw a graph that's the same shape, that's 2 units higher on every point from the graph given. And then you do that for all of those functions. Turn the page again. This is the same idea, but you start with an equation instead of a graph. So my equation is x squared. If I want to go up 3 units, what would my new equation look like? So it would be x squared plus 3. And then you verify it in your calculator by graphing x squared and graphing x squared plus 3 and say, yes, it did move 3 units up. And that's what you do on all of these. What would the equation for 26 be? If the original is 1 over x, the transformed one would have to be we're going to replace x with x plus 2. So it would be 1 over the quantity x plus 2. Okay? Good luck.